Today, we're going to briefly recap what we've talked about two or three times now about the process, the general process. We'll go through that faster since we've already seen it a couple of times. And then we're going to discuss the quantity development for general electrical and instrumentation, also control system sections of the scope of work. So, kind of backing up, basically the effort of quantifying is the process of converting drawing specs and lists into a quantity takeoff or an MTO. And again, the reason why we've got the variation here is you're using more drawings and specs if you're an FEL 3 and 4 or late FEL 3 and 4. And then some items, such as today's discussion, are more list based than they are drawing or spec based. Particularly if you're an EPC, if you're a general contractor, regardless, you're always usually pretty much left to having to quantify things on your own. So that means you're going to have to convert to one lines and those type of arrangements, those type of drawings to take off, which is a whole unique specialty in and of itself. Another reminder, and this will be the last time we talk about it, quantities represent material as well as installation activities, and they may represent more than one activity at any given takeoff or any given item. Quantities or key quantities are the items that are captured at the high level that we measure our ratios and metrics by. So, and there will be some discussion deeper into the weeds, I will say later, about that particular topic, because in E&I, there's a lot of things that are counted and a lot of things that are not counted, but need to be included within the discipline whenever you're estimating your costs. Again, we're talking about electrical and instrumentation today. The key quantity for electrical is lineal feet. The key quantity for instrumentation is each. So neat quantities are those quantities you take off directly from your drawings or calculate directly from your specs. The real life is what causes things not to follow that neat calculation. That's why we add the design allowances that we've talked about, or I call them design allowances, which we commonly refer to them as, but it's really design, MTO, waste, and overbuy. Those four components represent the allowances that we apply, and not all items receive the exact same allowance or include all of them. So the design allowance typically goes against the mechanical equipment and the electrical equipment, possibly against the instrumentation. The MTO allowance and waste and overbuy goes primarily against the bulks. Why? Because you either have a pump or you don't have a pump. You don't waste a piece of the pump. But then the MTO and the waste usually is related to how they're installing the bulk materials or how well the bulk materials are taken off. If you have a design that reconfigures the pipe in and of itself and causes it to grow, that usually is going to be a large enough change that it becomes a change order or a redesign, and it's not really considered a design allowance. So the we refer to them all as design allowance, but the individual components represent different things. You might overbuy cabling because you need 300 feet and it comes in 250-foot rolls. So you have to buy 2 rolls, or maybe it's 250 and 100-foot rolls. And you have to buy, in that case, you could buy exactly 300 feet. In the meantime, if you need a pump or you need a compressor, or you need a tank, you're going to buy that tank and that compressor. You're not going to have to, it doesn't come in packages of 3 pumps and you have to buy 3 when you only need 2. So you can see how the allowances, why the allowances would affect the different items differently. Again, the design allowance is something that's determined by engineering. It usually represents a change in material, a slight adjustment in capacity, maybe an adjustment in the orientation of the item, and therefore by the item changing its location slightly, it may have to move nozzles on on the shell of a tank or something. If that's the case, it really depends on whether or not you have bought the tank or not. But at the time that you're putting all this together, you don't know what's been bought and what hasn't in most cases. The long lead items will have already been purchased usually, but the rest of it has not. So you're basing your allowance off of the changes that you expect to happen before it's completed. And we talked about MTO, where it really goes back to who's taking it off, what's their experience, how much time have they been allowed. So the less time they have, the more they're going to be in a rush, or they're looking for shortcuts, and the tools and methods that they're using, which somewhat goes back to the shortcuts. If the tools may be consistent, but maybe they start rounding, maybe they don't have time to check, maybe they're doing more of a factored approach if there's no time. So there's at the time the MTO allowance is being considered, that's what everybody's stepping back and trying to figure out as you put those factors on, because you're at the end of the effort at this time when you're applying these factors. Waste in construction practice, we know what our typical construction practices are. We know that they're going to overpull cable and cut it and drop it. We know that there's going to be drops from the pipe left as they fabricate that can't be reused. And we know that people are going to accidentally buy more than they need of some consumable items and some bulk materials, either because it's a mistake and they ordered more, there was confusion and they ordered more, or you needed a certain quantity and the items are provided in something more or less than that quantity, and you can't buy exactly what you need. But the key is that allowances are not contingency, which is applied at a project level. It is a specific application to account for specific activities. And the reverse of that is when you get to your contingency calculations, they should not be considered any further because they're already accounted for. All right. So today, again, we're going to talk about electrical and then instrumentation / control systems. Those two names more or less go synonymous. So electrical, I think most everyone here is familiar with electricity, particularly, those of you that build buildings. The general concepts are very similar. It's just on a little bit larger scale, I would say. Uh, Depends on the size of the building in reality, but we categorize everything predominantly in two categories: electrical bulks and electrical equipment. So, like mechanical equipment, the design process, or unlike the mechanical equipment, this design process of the plant can move forward without all the electrical items being designed thoroughly. Mechanical equipment really represents the heart of the process, and then the structures that support it, the piping that transfer everything, work with that. The electrical follows that in the design process, because it's not until you know the size of your motors and the distance they are from your power sources that you can really size your cabling. And it's not until you know all that you really can start sizing your transformers. So there's E&I tend to lag behind in the design process because of the necessity for the motors and the lighting and the electric users to be identified fairly well. So the electrical equipment is usually pulled from an electric equipment list. if the design has progressed far enough for that list to be developed. If it hasn't, then we're left usually to conceptualize or factor. Um, I'm noting here that you can pull it from a one line diagram at times, but you have to be far enough along in the process for one line to have even been drawn. So you're typically not going to have a one line in FEL 2, and you may not have it in early FEL 3 either. It'll be mid to late FEL 3 that you'll actually start seeing one lines starting to surface that you can quantify from. So again, you're conceptualizing. So if you've got a program, you can use that. If not, you need somebody that has a strong electrical background, or you're going to be doing some very high level factoring. But in each case, all the items in electrical really fall under unit of measures that are either each, pieces, possibly lump sum, or lots, or lineal foot. Well, the electric equipment would not be lineal foot. That would be the bulks. So some of the a good sampling of electric equipment can be broken down into switchgear, starters, variable speed drives, transformers, power distribution centers, which normally if they're stick built, then all the interior items will come separately. The building we built, and then you'll install your switchgear and your panels and your starters and so forth. But if they are modularized, then usually the switchgear and panels and cabinets already come pre-installed. You just need to unpackage them once the building arrives. If the building's large enough, it'll come in sections, and you'll have to actually assemble the building sections, and bolt it together, seal it up, make sure that it's watertight, and then you'll install the HVAC, exterior lighting, stairs and platforms and so forth. Normally those most of the PDCs that I've seen installed usually sit on foundations that keep them elevated. Some are neighborhood of 4 to 6 feet above grade, so that the cabling can enter from underneath. I have seen a few occasions where they actually build a pit or a vault underneath it, so that the building's sitting at grade, but all the cabling is still entering from underneath, but it is entering through that vault. There are some occasions where you'll run into where the PDC has the cabling entering from the side, but that then requires the orientation of the switch gear and panels inside to change, so that it will allow the cabling in from the side to then move around the interior of the building. Versus when it comes from underneath, you can put a bank of switch gear on either side of that opening in the floor, and then it'll come up through the floor and then enter the back of the switch gear, the panels, the cabinets. And then if those items that need to move to the panels, that can be wired to the outside walls. And so you've got a walking path that kind of circles that center. It's not as easily done whenever the wire is coming in from the side. Motor control centers, pretty much the exact same thing. It's just that the switch gear and the motor control centers are different than the motor control than the main switch gear and the power distribution. The motor control center is where all of your starters and variable frequency drives are going to be located, versus the larger switch gear that turns your power on and off and sends it to its different areas. Occasionally you might see a PDC on one end of the structure and the MCC on the other end, if the process and plant's small enough that you can fit it all in one building. Typically, my experience is that they're in different buildings, and you've got one or two main PDCs around the structure, and then the motor control center is spread out by unit close to where the buildings are. I mean the motors are. I don't know what that is. That's odd. Can y'all see those lines that just showed up? Or is it just me?
I think you got your highlighter selected.
Yeah, I see it.
Somebody selected
Mhm.
annotate and made a note.
Yeah, I mean, all I did is accidentally bump the mouse. I didn't click anything, and it just showed up. So
Yeah.
that's somehow it's operator error, but I don't know exactly how.
You might have it turned on where it's interactive and other students can, and somebody might have been fiddling around and not realized what they did.
I'm trying to do it, won't let me.
That's because right now I'm grabbing the mouse and moving. It's not doing anything. So that's interesting. Okay. Yeah, it may be turned on. So somehow it's accidentally there, but we'll continue to talk.
It's probably the Zoom fairy.
Here we go. That works for me. So similar to the mechanical equipment, the electrical equipment is going to be identified off a list if we aren't forced to take it off of one lines of some kind, as I was saying earlier. I've talked about this here a few minutes ago that in FEL 3 and 4, you might have the one lines to take off, and if you're in a small contractor, you're going to be forced to. Because whenever I've been with the smaller contractors, the engineers never offered or provided us quantities. But working in an EPC, honestly, we get a little bit spoiled because the engineers are always saying, "Here's your list," and then we just have to take that list and then labor and price it. Sometimes they can provide pricing, sometimes they can't, but they can definitely define what is needed. But in FEL 2 and 3, nobody really knows at that point in time. So the factoring or the modeling may be done by engineering, or it may be done by estimating, depending upon what programs are available in each group and who has the time. This is an example of an MTO for electrical bulks. So you can see here it's covering power cable, control cable, grounding cable, conduit for both control and power, some control stations. So they're basically on and off buttons, and then cable tray. The from a document like this, you can quantify. You know how many feet you have here. For example, you have a 3 conductor 4-aught with the ground. You have 400 feet. So that would be your quantity input. Same with the control cable here. On this one here, you can see where they have the number 2 in parentheses. So it's 1,150 feet of that 3 conductor 500 MCM. It says KCMIL, but it's same as MCM with a 5 kilovolt ground. But there's 2 of them. So that means there's actually 2,300 feet total, but you have 2 cable runs. That's important because they're quantifying the materials for you here, but there are things that they aren't quantifying, such as your terminations. So if you know this is a 400 feet of that cable, that's basically 1 run. While this here, there's 2 runs. So you would have 4 terminations on each end twice. So that'd be 16 terminations instead of just 8. So you can use this to by knowing how to read this, you can figure out how many terminations you need, because that won't be in your unit labor that you would apply. But this is a pretty simplified list here. They may not have many more quantities than this as far as categories, but if this were a real job, it would be 20 pages of this instead of just 1. So what are some of the items that are to be included within an electrical MTO? You've got the wire and cable, which I just showed you. That represents power cable, control cable, lighting cable, utility cable. Also, if we go back, it had grounding in there. So we have our grounding cable here. It doesn't show, this particular list doesn't have lightning protection in it, but lightning protection could be in there. And if you notice, I'm making a note here that the wire and cable are part of your key quantities. Grounding and lightning protection are not. Even though they're cable, they're not. And the primary concept is that the cable that you are keeping as a key quantity is the cable that's going to be carrying a current on a regular basis. Grounding and lightning protection will only be carrying a current if there's a lightning strike or there's a short or something of that nature. They're not directly affiliated with the process. And most of all of your key quantities are really focused on, do they relate to your process? Because the process is what drives your cost. And that's what, makes the difference between this chemical plant and that refinery and then the next power plant. They all three are producing something very different. So they have different ratios and they should end up having different. So the grounding, as you use your key quantities, which are driven by your process, the grounding and lightning protection kind of get rolled into the results of your key quantities. Conduit, cable tray, those are also going to be in length, just like the cabling. But as we said earlier, your wire and cable that's to be counted as key quantity should be in lineal feet. Your grounding, lightning protection, conduit, and cable tray, they're also in length, but they should be in something other than lineal feet. They should be in just feet, or maybe lineal foot conduit, lineal foot tray, lineal foot grounding. So it's an LFC, LFT, or something of that nature instead of just an LF. And consequently, your system will know not to count it because it's looking for that LF as your primary key quantity unit of measure. Light fixtures, power panels, distribution panels, circuit breakers, switches, they're all each. So they won't be pulled into the key quantity. You're good there, but it is important to know that they are part of your bulk materials. Non-structural supports, and it's unistrut and all thread and similar type supports. Terminations, there is a material cost with it that's primarily an activity. On the smaller cables, the large cables are actually quite involved. The termination kits for large cable can be pretty extensive. And then you got smaller bulk materials like grommets, lugs, washers, RGBs, and seals that are all part of that electrical MTO. So, as I was mentioning earlier, if you're part of an EPC, your engineers are going to provide you an electrical list, a line list, and then they will likely provide you the tray and conduit and other related items as I showed you in that one list. As you move back from FEL4 to FEL3 to FEL2 and things become more general and factored, you're going to receive less and less. But if you don't have a list and you're provided an instrument electrical one line, this is an example of part of something you might receive. And from here, there's a lot of work that you have to perform. So it will tell you what your motor size is, and it'll tell you that you have a line. It'll show you where your transformers are. It'll show you where you have switches, but you really need to be versed in reading these to be able to deal with it well. You'll have to use plot plans and locate where these motors are to come up with your lengths, because you'll have to figure out how you're going to make a run from the location of that motor through your pipe racks and your conduit to your pipe racks, down your pipe racks to the PDC or the MCC that's powering that motor, and then from the MCC to the PDC that's providing the power to the MCC. So you'll have one lines for the plant showing where all the motors are and what they're connected to. And then you'll also have one lines between the PDC and the MCC as well. Now, I think we've got a couple people in the group that I think are fairly electrically well versed. Do y'all have anything you want to add to what I'm saying?
The PDC would power the MCC. It wouldn't go to like each little bank. You know what I mean? Like the MCC, each motor would have its own little box, its own little bank, and the power would come from the PDC to the MCC as a whole, not to each motor. That's
Right.
why it's separated out by unit.
Right. So that's why I'm saying that the PDC you'll have a one line from the PDC to the MCCs, because basically all the MCCs require a certain load, that power load is going to come from the PDC to the MCC. If that MCC needs several, then it'll have several lines coming to it. Right. So
That's right.
if it's running 120 for utility, it's going to have a 120 line coming, unless it actually separates it in the MCC and then steps it down with a small transformer there, and then powers the 120. Most everything's running at 600, except for your large motors, which you can see one here where it's 240. This 1,000 horsepower motor here is running quite a bit higher than 600. It looks like 2,400 volts. What it looks like.
Usually we wouldn't let anything over 480 be in the same MCC. It would be 480, 240, 120, and then the bigger stuff usually gets separated out and put into its own MCC with higher levels for entry and work inside of it.
Good points.
So actually, Professor Whitman, going back to that drawing.
Yes.
So I've noticed on a couple of the projects that we've done so far, we haven't had like a symbols page. Is there drawings that we're going to be doing these takeoffs on that have that force? Because some of these symbols I don't recognize from the commercial side. These may be more symbols that like electrical engineers use on industrial projects.
Well, there's not going to be a task for electrical. We're not going to take all that off.
Okay.
Because it is more specialized, and I thought that was really, to try to dive into that was going to be beyond us here. So there's in the development, but that is a true statement, that there should usually be a legend or a list of your symbols whenever you receive a set of drawings. There usually is one with PNIDs. There usually is one with other sets of drawings as well. And same with one lines. It's a good point. This is actually another sample of some MTOs. This is a more generic. It's showing the switch gears and how it's described and also quantified. So in this case, if you receive something like this, you would know that you've have the transformer and that what size and the parameters around it, as well as a separate grounding resistor, capacitor bank. This would define some of your switch gear, and then you have your quantities here. So you would input these, and then, but because you have more detail with it, you can then labor it. But this is an example of a electrical equipment list versus the bulks that we had earlier. So again, this could go on and on. If you have multiple transformers, I mean, today I was in a meeting and it's for a hydrogen plant, and it had 14 transformers feeding in to the common PDC. Here we're just showing one, so it could grow quite a bit. You could have depending on how many motors you have, your MCC switchgear, your PDC switchgear, and your MCC starters and cabinets could be quite extensive in this list. Here we're just showing 5, but it does give you an example of what you might encounter. The other thing that you would hope you would receive, if not with this list from procurement later, is a price per each one of these items. Now, any general other questions or topics you'd like to discuss along the lines of electrical? So like I said, I don't have a electrical MTO task with the estimate, the representative estimate that you're building. The items that you're not quantifying yourselves are going to be pre-built into the template. And so it's just the 4 MTO tasks that you'll be dealing with for the class that represents, a sampling of the activities that you would need to perform.
I don't know if you were planning on talking about from the MCC to the control room.
Well,
and VFDs and split range.
I wasn't going to go into them in detail.
Okay.
I didn't mention that they were there. The control cable, that's a good point. We could dive in a little bit deeper. But if you go back here and you're looking at your bulk material list, the power cable is what's going to be either bridging the power to the MCC from the PDC or from the MCC to your motors. So that's what this power cable is representing. It may also represent your lighting cable because it's power. It's not control, but it's going to be small. Your 3 conductor 12 gauge down here, very well. Well, it's 600 volt though, so that's not lighting. So they might give you a separate breakout in here for your lighting utility cable, or if you're running through here and you see you're dealing with your 10 and 12 gauge and it's dropping down to 120 volt, now you're back. Now you're in your lighting and your utility. This 600 volt, this is all going to be process equipment. On the other hand, your control cable, this is what Stephen's discussing. This will run to and from the instrumentation back to the control room. And the instrumentation is either going to be sitting on a skid, sitting on a piece of equipment, or sitting in pipe, or it's going to be next to it and connected to it in some manner.
Same thing with that HOA right there. That'd be on the skid.
HOA.
The control station description.
Oh,
HOA.
Yeah, these will be, well, they could be skid mounted or they could be mounted on a post next to an item.
Right.
But yes, yeah, exactly. And that's going to be a quick off and on start button, stop button. So if there's some type of, I was going to say if there's an emergency, but if there's any reason that you need to stop that motor remotely instead of waiting for something else, I say remotely, manually, while you're there at the motor versus having to relay back to the control room and have someone shut it off remotely. That's how you would do it, was through that HOA control station. The grounding cable, like I said earlier, that's not a key quantity, while these are. but they're quantifying it here. There's going to be a grounding loop throughout the plant. There's going to be a loop around it, and there's also going to be a grid that runs through it. And so your equipment and your steel will have what's commonly called a pigtail that will bolt to it, and then it will run away from it down the foundation into the ground and tie into your overall grounding grid. And then that grid itself, even though it's buried in the ground and could be grounded in and of itself, there are rods spread out throughout the grid that are usually somewhere in the neighborhood of 10 feet long, as shown here. And it's showing it's a 3/4 inch diameter. They're driven in the ground to a point where they're not seen anymore, and they're taking that current deep into the earth. So if there's a short or whatever, then that is what's going to direct it away from everything else and take it to the ground. Similar but different would be lightning protection, where you have your lightning rods at the high points of your equipment or your structures, and then that copper cable is going to run down the structure and then tie into the grounding grid as well. The conduit, as you can see, they've called out the control and power conduit separately, but it is accounted for. And often you're in the field, your conduit is going to run from where the instrument or the motors are back to your pipe rack. Once it gets to your pipe rack, it will then jump into a cable tray, and then the cable tray will run from a central location back to the MCC or tie in between the PDC and the MCC, if depending upon what the run is, right? So if it's running, the wires running between the two buildings are going to be on one set of cables, and then your other cables will be running from the MCC to the motors. The exception with what I just said would be is you do have cable tray or tray that drops down to 6 inches wide. So they can be, 36 inches, 24, 36 is pretty common. They can be 42, 48 inches wide, and they can be as narrow as 6. So you can run a handful of cables away from the main pipe rack cable trays in stepping it down, but once it leaves the tray, it's going to enter conduit until it reaches its final destination. The cabling is, it's not like you go into the attic of your house or possibly, some buildings, depending upon their design. Everything, all cable is in some form of protection, unless it's actually an armored cable and designed to be non-protected. Oh, let's see. Anybody have any other questions about it in general? A couple other items, and that is your lighting. Unlike your lighting is going to be running in a separate set of conduit. So again, it's 120 volt, so it's not going to be running in the same conduit and likely not even in the same tray as the 600 volt and higher cables. And then those cables will be separated if there's a great enough difference as well. But the lighting fixtures are running on their own set of circuits, and the panels are separated. So, and that's really going to be driven by your requirement for area lighting. So inside of your open structures, you're going to have a lot of lighting. And then once you move out of your open structures into your open plant, each facility is going to have its own standards of what how many lumens that it wants in certain conditions or certain areas. And so you have to have enough lighting to support that. And so that's what's going to drive that's going to drive your number of fixtures, that which then will drive the size of your panels and how much cabling you are needing for that particular area. Same with utilities, with your industrial receptacles for utility support spread around the plant itself. Does that make sense, or does anybody have any questions?
That makes sense.
So if I'm not, if I need more explanation, we can talk about it. If not, we'll move on to instrumentation. All right, so instruments, the term instrumentation and control systems kind of flips back and forth within the construction industry. Some companies call it instrumentation, others like to call it control systems, but regardless of whatever they use, there's going to be three general components that are included in that category or in this discipline. The two primary ones are the instrumentation and the control systems themselves. The instrumentation is the device that's actually taking the reading, while the control system is the program and hardware that are receiving that reading and determining what to do with it, how to control the plant with it. And then instrumentation, I said three, and that's two. The third one comes in is that when you get to focus on instrumentation alone, like electrical, it breaks down into two different components. One of the components is the instrumentation itself, and the other component, which makes the third that I mentioned in total, is the support and connection materials. They're kind of the bulk materials of this category, and they're usually called just instrument details. So I'll show you some examples of that in a minute. So for those of you that aren't too familiar with instrumentation, these are the items that it represents. It can be pressure gauges. It can be differential pressure gauges. So in other words, if you have an instrument that's determining what's the pressure inside of a pipe, it's just telling you you're at 100 psi. But if you have a pump and there's a pipe going in that's 75 psi and it's coming out the other end at 125 psi, you'll have an instrument that's tied to both of those lines and then measuring the difference between the two, because maybe the design is they're expecting a 50 psi increase coming out of the backside of that pump. If it's only generating 30, then they need to address that situation. If it's generating 75, they'll need to address that as well. Maybe they need to dial something down, while the other one could be a sign of slow failure, or they just need to dial something up. Temperature gauges and thermal wells and elements relate to temperature gauges. That's why they're there together. But in some cases, you can put a gauge right on top of something, a line, a vessel, or whatever it may be, and it's all self-contained. There's going to be an opening that you can screw that temperature gauge into, and it will tell the temperature, just like a thermometer will if you're sick. On the other hand, thermal wells and elements, if you have, and that's usually used in a fired environment, but if you have a number of points that you're wanting to capture, then you'll have literally a well. So you bolt this on to the wall of the furnace or the heater or the vessel or the pipe, and that well penetrates inside, and then the element slides inside that well and then screws in tight and sealed. So the thermal well is actually taking the heat it's enduring the environment of whatever it's installed in, but the element is what's sensitive to the change in temperature, and then that element sent through a wire sends either sends the heat back to an instrument that will read it. And so the instrument could be some distance away from that particular thermal well and element. A good example is that in older cars, there's a temperature gauge in your car dash, but that temperature gauge is reading the temperature of the water inside the engine. And there's literally a wire that runs from the back of that gauge through the dash, through the firewall of the car, and used to drop in and tie to an element that was screwed into the manifold of the engine, and that wire was transferring the heat. It wasn't electric. It was transferring the heat from the engine block to that instrument. But that instrument was designed to read the heat that was being sent to it and account for the drop in temperature due to the distance and so forth. This is pretty much the same concept.
Well, thermal wells allow you to change out instrumentation without shutting down the equipment, because you wouldn't be protected from process. If you had to change that instrument, you'd have to shut it down, clear it. So the thermal well gets you around that.
Yeah, very good point. Very good point, Stephen. And I use the example of screwing in that temperature gauge directly into the pipe of the tank, and it tells you what the temperature is, versus the thermal well. And like Stephen's saying, that thermal well, it's threaded in and sealed with the shell of whatever it's in, and the element can go in and out without opening that. But if you go back to what I said about that temperature gauge, if you remove that temperature gauge, you've opened up the system. And so whatever gas or fluids in that system will start coming out of that hole. So the thermal well assists in that process. So that's a very good point. Thanks for bringing that up.
Yeah, oil and gas, you don't want it outside the pipe. Just FYI.
No, chemicals either. Roman Haas produces some chemicals that is highly flammable just when it comes in contact with air. It explodes. So
yeah, that's what we work with. It's called Pyre Fork. It comes in TIL, triethyl aluminum. It's what we use to make plastic.
Very, very explosive. Very
yes. Can't put water on it or air or anything. Blow up. Bad stuff.
Bad. Yeah. It's there's a lot of chemicals in the petrochem world that are just, it's not like gasoline we pour it out and you go, that's bad for the environment. It's stuff like it you don't smell it, but you're dead. Or
hydrogen sulfide. That's why they put that egg smell in it, but it's really too late anyways by the time you smell it.
Mm-hmm. It's the stuff you can't smell at all that leaks out that doesn't have anything in it that scares you once in a while. But yeah, good points. Flow meters and indicators. Literally, it could be a rotometer, it could be an orifice plate, but you have different style of instrumentation out there that are basically determining what the flow of the gas or the liquid is through the lines. The indicators are actually showing what that is while the other one's measuring it. And then I note down below, transformers, you can have a pressure gauge, you can have a temperature gauge, you can have a flow gauge, but they're just measuring what the environment is. The transmitter takes that information, converts it to a signal, and sends it to the control room. So that's how the control room's receiving the information. You have vibration meters, load sensors, on and off switches, actuators. So if we talk about control valves, it's a valve with an actuator on it. Most of the companies I've dealt with consider control valves actually instrumentation and not piping. Manual valves are considered piping. The valve itself is the same, but the actuator is what makes it one or the other. The reason being is that if you've got a manual valve, you manually go out there and you open it, and you close it, and you do what you have to. But if you have an actuator on it and it becomes a control valve, you can operate that from the control room, and you can monitor and adjust flow rates from the control room versus having to send somebody out to take care of it.
You
And
also have split range controllers.
what do you mean?
So let's say you got two chemicals that are mixing and you have to keep it at a certain ratio. So you have a rotometer downstream that can measure the ratio, and it can open and close either one of the valves to
Mhm.
either feed more or feed less.
Oh yeah, that makes total sense. Well, and along those lines, I'm mentioning an oxygen sensor here. So it's an instrument that's measuring the amount of oxygen, along with uh, what Stephen's saying. You know, they're in that case, the way he described it is that they're monitoring the mix of these two chemicals by flow, but you also can install, and I'm noticing here saying more, and some of the more is analyzers. So you can insert analyzers into a line or a piece of equipment, and then those analyzers will then tell you what the component or what the makeup of that gas or fluid is. So it's analyzing the contents. So based upon these different, there's normally not just one way to do things, and unfortunately, there's also not one way to call things. So what one company calls something, another company will call it something else, but they mean the same thing. It's just two different names for the same item. So that creates a little bit of confusion in the industry, but that's just life because we don't all talk exactly the same either. It kind of extends from that. But that's a sampling of the instrumentation that we're talking about. Let me back up quickly though. When I mentioned vibration meters and load sensors, you know, you're rotating equipment, if it's balanced right, if the alignment has been done well, and if it's in good shape, will run reasonably smooth, just like the engine in your car. If it starts having problems, it will start to vibrate. The issue with that is that some of these items are moving or spinning so quickly that if a vibration starts to kick in and becomes too extreme, it'll come apart. A good example of that is like a gas turbine. Gas turbines are spinning extremely fast, and so you have to be extremely precise and have those things balanced well. So the vibration meter will start to tell the operators that we've got an issue going on here because vibration is starting to pick up. Load sensors, that could be a couple different things. You could be measuring the weight of something. So say you've got coal coming in on a conveyor belt, you got a load sensor that's reading the weight of that coal. Now they can tell how many tons of coal they've moved in an hour or a day. But you also have a load sensor where if you've got a rotating piece of equipment and the load starts to shift on one side or the other of this skid base, then normally if it's 5149, kind of split in weight, and all of a sudden that starts shifting to another side or starts getting worse and worse, you've got something going on. It's torquing somehow, and you need to go investigate, because if you got vibration or you've got torquing going on, your equipment is in need of maintenance, if not replacement. So and then on top of that, you've got software. We'll talk about that here in a second.
We also use a lot of the load cells for the rail cars that we load, because there's requirements, federal law, that you can't exceed certain weights on rail cars when we transport chemicals.
Yeah, good example. And so they're all tied into the control system overall. Every one of them. Now, standard items that you'll find in the instrument details. So you've got stands, supports, bolts, washers, nuts, connectors, base plates, flex. I'm noting flexible conduit. You could have rigid conduit, but most examples are flexible. Tubing, small valves, not, they're all going to be 1/2 inch, 1/4 inch. They're not going to be too many large valves because those are in the piping system. Minor piping fittings, wire jumpers, and even grout. So, like I was saying earlier with the electrical, as you move from FEL2 to FEL4, your way of identifying, quantifying, and estimating these are going to vary. Because, like I was saying, electrical and instrumentation, they tend to be designed. The designing of them is performed later in the process, not earlier, because you need to identify what the equipment is first, get the weights, and then after you already figure that out, you can start determining what the motors are, and that will then drive your electrical. Instrumentation usually kind of we always tease them about bringing up the rear. They're one of the last things that's completed. So that means as in your earlier stages, you're really purely factoring or conceptualizing. So, and I know I keep mentioning it's kind of repetitive, but there are software programs out there that have the capability of modeling these things with very little data. I've mentioned AspenTech ACE, ACCE, and I keep mentioning that one program because it is the one program in the industry that is capable of doing this at the scale and detail that it is. There isn't another estimating or design program out there that can do what it does. Smart Plant 3D and some of the other programs exceed it in its detail and exactness, accuracy, but those are design tools. While ACE is actually it's a modeling tool. It's a conceptual modeling tool to fill the gap until engineering can bring the design and the actual model along to a point where it can be utilized. Once you move out of FEL2 and FEL3 and you start to have P&IDs that are far enough along they can be used, then the P&IDs, if you don't have an instrument list, but you have a set of P&IDs, you can make an instrument list because the P&IDs they illustrate all of your instrumentation, and it shows how they're even related to the pipe and to the equipment, because it will illustrate where they are. By the time you get to FEL4, if you're in an EPC, you're going to receive an equipment list. And even if you're not, you still should receive an equipment list, if not a set of P&IDs to build your own. So it's not quite like electrical where you have to generate your own quantities off of a one line schematic that's can be somewhat challenging. And then the drawing details, there's normally a standard set somewhere. Somebody, either the client or the engineering company, and maybe even the contractor themselves, everybody has their own rendition of what the instrument details should look like. They have their own numbering system. They have their own sets. But if you were to take them all side by side, they may not be identical, but you'll notice they're all actually quite similar because they're all modeling a standard approach to installing start stop button on a stand, or supporting a transmitter off the side of a pipe, next to a orifice plate that's reading the differential pressure between each side of the orifice plate. So there's only so many ways you can do that, and so they're all quite similar, even though they may be different or owned by different entities. This is an illustration of a P&ID for those of y'all that haven't seen one before. I know for Stephen and a couple of others, this is nothing new. Apologize for it being a little bit gray, not too dark, but each one of these bubbles is an instrument, and when you look at them closely, if you see a PI, it's a pressure indicator. TI, it's a temperature indicator. FE, it's the flow element, right? So you can look at the name and you can tell, or the not the name, but the symbols, and you can read what it is. Some of them are hard to memorize because they're actually indicators, or they may just be an alarm. They may just be a light on a panel. So if it's square, if it's a circle with a square around it, it's in a panel somewhere. Could be back in if it's a solid, if it's a actually at this moment I'm blanking. If it's a dashed line, I believe it's a local panel, and if it's a solid line, it's back at the control room, or I may have that reversed.
That's right.
So
then you see it connect to another one, like the one at the top on the outlet. This looks like a degas column or distillation column. So those 3 indicators right there are all sending a signal back in house.
yeah, so this is back in the control room, I believe, and that's the element. That's a temperature element. That's a temperature transmitter. And so if you looked at it, it'd be TI or TE, temperature element. TT would be temperature transmitter, and it's sending the signal back to the control room. Now, what's not showing here is that some plants are moving towards installing what we call a charm, and it converts from a digital to light. So we can collect a whole number of wires with digital signals on them in this area here, run it to a charm, and then you might go in with 50 and you come out with 5 optical cables, and that runs to the control room, and the control room then reinterprets it and then sends the signal wherever it needs to go. And the concept is that now, instead of having 50 wires running around there, you have 5 cables. And even though the optical cable is more expensive than the wire, 5 optical cables are a lot less expensive than 50 electrical wires. So it cuts down congestion, and it cuts down on cost in your long runs from your process units back to your control room. That's but that's the signal's going to have to get back to control room. One of those methods, either you've got home run electric cable running all the way back, or it's going to be converted, and then the optical cable will take the signal back. But you can see here, you've got instrumentation that's attached to the piece of equipment itself, and you've got other instrument here that's attached to the pipe itself. One that I did not mention in that list earlier, but you can see in this drawing here, it's hard to read, but it's a PSV. It's a pressure safety valve. So this line on it right here has a valve on it that if the pressure of whatever's in it exceeds the capacity of the system, it's going to fail by design and release the pressure. And there's 2 types. There's one type is that once it fails, it has to be trashed. And another one, when it fails, it can be reset and reused. But either way, it's if the whole system's designed to handle, say, 120 psi, that thing will be designed to fail at 118 or 119, something really close, but just before the system goes, because you don't want the system. It's better to lose that in a controlled manner in a location that's designed to handle the release than it is for the system to fail as a whole. That can be extremely detrimental.
It relieves into that pipe to the flare, probably not to atmosphere though.
Yeah, yes, and that's because you've got a flare header right here, so that's a good
Yeah.
point. And I've seen some that released atmosphere, but they were
Non-hydrocarbon.
it was an item that could be released without damaging the atmosphere or killing anything.
Blowing up. Yeah.
Yeah, hydrocarbon, all the things that we mentioned before, the acids, the hydrocarbons, all of it. It's not positive.
It definitely looks like a degas column.
Yeah, I think the original design had something like 40 trays in it.
Yeah.
I don't think it had any bedding in it, but any questions from anybody so far?
No, right up my alley. I'm happy.
All right. And one other thing noted right here, there's this line here. This is actually a spec break right here. So this pipe coming in here and that pipe going there are actually two different specifications. They may both be 6 inches in diameter. They both may be carbon steel, but they're going to be a different grade of carbon steel, or maybe one is carbon steel and the other one's something else, stainless steel or something. But there's going to be a
CS11 or CS12.
Yep. No comments. Okay. Here's an example of instrument details. So this is literally just showing this support and how it's going to be anchored to a concrete slab, while this one shows the tubing and how the instrument's going to be connected to two different places in the pipeline. And instead of forcing you to quantify the tubing and the valve and the other items, the plugs and unions and whatever, this actually quantifies it for you here, as you can see. So each instrument that is identified in the equipment list or the P&ID will have a instrument detail assigned to it if it's required. If you have like the example I gave earlier, you have a temperature element or pressure gauge that threads straight into the pipe, there is not going to be an instrument detail for that, because the OLET that the item is, that the instrument's screwing into, threaded into, is all that it needs. And so it's just going to thread in, read, and then you'll see what it's reading right there at the gauge. It's going to be a local gauge. But if these were standing on a support next to the pipe with a thermal well and an element or something like that that's reading it and then taking it to the instrument, you're going to need a support stand. Now you're looking at a detail like this. If you have, I mentioned an orifice plate with a differential pressure or a flow indicator reading it, you're going to have something more like this. Because with the orifice plate, it has a hole in the center of it, and there is I'm going to blow up his name. But Steven, you remember his name? It's a scientist law that.
Oh, I'm lucky if I remember my name.
That's something like Buscellini or Bocelli or but he
Buscemi? It's a good
What?
actor. Buscemi?
Yeah, no, not him, but there's he's got a law that says if you got an orifice and between that orifice you have a differential pressure of this and that, and you know the thickness and the size of that orifice, you know you can calculate mathematically the flow of the gas or fluid through that line. Versus if you put in a little rotometer, it spins and it now does a volume calculation by the velocity of its spinning and knowing the size of the pipe. But Bucciolini's theory using that orifice plate effectively does the same thing. But to do that, you need to have an instrument, you need to have this cabling that's tied into the pipe in two different locations. So if you have something like that, you need a detail like this. And if that instrument happens to be on a stand, you'll need both. And the list will tell you both. So what you need to do, or the estimating team needs to do, is quantify and price all the items in this detail, labor it, price the materials, and create an assembly value for it. And then every time that you identify an instrument that requires it, you apply that price. So estimate it one time, apply it as many times as you need to. Is
So
the
that's-
approach.
That one on the right is an impulse one. You see how it has those little valves right there in between, like the 1 and 3, has one on the side, one on the top, and one on the other side. The flow comes through there. You can block those two, close those two on the sides, and open that one in the middle, and then to back flush that transmitter, and then you can line it back up the right way and get your reading back. Like if you're reading drifts, that's how you back flush it to get it going again.
Yeah, I understand.
It
Kinda
was
like-
Torricelli. It was Torricelli, Torricelli.
Torricelli?
Yes, sir.
So not Buscemi.
No.
Not Pacelli. Maybe I'm thinking of Andre Pacelli. We're listening to him and Sarah Brighton the other day. So those people are incredible. But no, thanks. That's good to know. It sounds like it's like a fixed filter, a fixed media filter that has a backwash system to clean it out. The way it's operating. But you're going to need, that's how you want to approach each one of these details when you're working with your instrumentation. Now, on the other hand, you have the control systems, right? So we have these instruments all throughout the plant, and they're tied into the equipment, they're tied into the pipe, and they're reading the environment, and then they're sending a signal to a transmitter that's then transmitting that signal to the control room, either directly through electrical or through optical. And some, well, used to, I don't think there's any pneumatic anymore. There used to be all pneumatic decades ago. But now the control systems is what's receiving that signal in the control room. And it's feeding in, and the control system is supported by a whole myriad of programs. But the control room is sitting on top of a number of computers, and the operators are watching the plant through these screens, which technically are human machine interface components. A lot of them are touch screen now, and they even have really realistic diagrams and symbols for the pieces of equipment. But the programs all together are designed to pretty much run the plant without human interface, but you have to have humans there to override the system, because the system doesn't know what to do at all times. So in the end, it still falls back to humans, but the programming takes care of a lot of the daily redundant readings and decisions, and then waiting to be overridden by the humans that are in the control room.
And then you got there's two different types of control room environments, you have the PLC, which is project or process logic controls, which is where you tell the computers what all you want this process to do and its parameters, and the computer runs it and stays in there. And that's what we drive to design plants to, is remove the human factor. And then if there is a human factor, then it's usually ran through a DCS, which is digital control systems, which is touch the touch stuff, the stuff that you manually have to interact with.
Yeah, the distributed control system.
I'm sorry, distributive, yeah.
Yeah. And then talking about PLCs, you know, one thing I was saying, well, I'm going to move on. Let me run through this first and I'll make the point I was going to make. And that is a sampling of some of the systems or integrated control and safety systems, the distributed control system, safety instrumented system, fire and gas detection and protection, instrument management, alarm management, machine monitoring and protection, condition monitoring, analyzer data acquisition, custody, metering. So, you know, when you look at this, and there's a lot more programs that are all built into these control rooms now. And think of it like this, where you have Windows that is running your computer and it's sitting on top of machine language, and then you have the programs like Excel and Word and PowerPoint that are doing specific things. And so some of these programs are the programs that are kind of maintaining and driving the whole system, while others are focused on specific activities like fire and gas or managing alarms or monitoring the equipment. So if you have one system saying, hey, we've got a problem, it'll interface with another one, like fire and gas will interface with the AMS, and the AMS will then tell the alarms what to do. But the fire and gas is what detected it and said we need to do something. You know, so it's extremely complicated, and therefore a lot of these systems here don't fall back to your EPC companies. Your EPC companies normally will call in a specialist to deal with all these different programs and systems. So some examples of who those people are: Emerson, Johnson Controls, ABB, Rockwell, Honeywell, and a few others. Those are the bigger names there. They will take all the instrument information. The instruments are designed by the EPC company or the E company if they're not an EPC. And then these companies will analyze the IO counts and start building a system architecture around what the plant's supposed to do, looking at all the IO counts that are coming from all the in out signals from all the instrumentation that's out there. Meanwhile, they're also talking with the client, because the client's going to say, this is what I want the program to do. This is how I want it to operate. And so once they start getting an idea of the IO count and the architecture that they want to put together, they can start also determining what hardware they're going to use, what server, what computers, and cabinets and so forth. And then they'll design it all. But they already have kind of shells that represent the general system, but the shells, it's kind of like Excel, where the shell's somewhat populated but somewhat empty. And so once they start learning what is being designed and working it into the architecture, and then they're working with the client on how they want it to be, then they can start filling that shell with specifics. Some of that they can build before they arrive to the site. The rest of it that they will actually program. They'll install the hardware and finish the programming at site, specific to the job itself. And it could take 1 to 4 months 1 to 6 months to program it, depending upon how big and complicated.
All right. See what he says. Give
That
him 2
makes
minutes.
all right.
Oh,
That's
Thank you.
what I have today for electrical instrumentation and controls. Again, we're not going to have a task oriented on this. I'm basically covering it because it's one of the major disciplines, and I wanted you to have some more background around it before we moved on, even though you're not dealing with it specifically. Any thoughts, questions? Appreciate Stephen your comments adding to what I've said.
I'm just happy to talk about something I know.
I understand.
You sound like a broken record.
At least I'm playing the same song. Just the one I like.
All right. So no questions, comments. Today,
Do you I have a question actually. Do you typically encounter these like in construction, or is this just like a subset of like industrial construction only?
well, what the E&I scope?
Task 4.
Yeah, we deal with it virtually every
We
single
don't have a
project
class.
work
We
on.
just kind of work together, right?
Yeah, we
Okay.
Following Thursday.
David, hit your line.
every job has E&I in it. Now, not every job has control systems in it, because if it's
That's what I meant.
if it's a small enough project, we're probably just tying into an existing system, and therefore all we're doing is picking up the instrumentation, the power cable, the control cable, and if we're installing a power cable, and if it's just utility power, we're just tying into a panel. But if it's a new motor, then it also means we're installing a motor starter somewhere. If there's an open slot in the cabinets for, because they usually have spares, we'll drop it in there. If the cabinet's full, we'll have to bring in a new cabinet and put in a starter that way. But if it's a large plant that pretty much it's new, standing on its own, yes, every single one is going to have control systems in it of some kind, depending upon what's required. Good question. So what was due today at 6 was task 3. That was the building effort. And this Thursday is another open session class. You'll have all class to discuss and work on task 4, which is the piping takeoff. Now, task 4 is not going to be due Tuesday. The cycle's being broken. We're going to confuse Whitney again.
Sounds like a Lord of the Rings quote.
Yeah.
Cycle's gonna be broken.
Oh no, I'm prepared.
We
I got a
Tuesday,
dry erase board.
Monday and Tuesday, there's no classes at all. It's fall break. So like myself, most of you get to enjoy just a day of work instead of a day of work and school. I mean, for those that are just students on the call, then you'll have Monday, Tuesday off. But because there's no class on Tuesday, that means that our next lecture that would be on Tuesday will now be next Thursday. And so that's going to start our new rotation of lecture on Tuesday, open class lecture on Thursday, open class on Tuesday. And we'll do that until Thanksgiving.
Hey, Professor Whitten, can I ask a question that I should probably ask on Thursday?
Sure.
Sorry,
Depends on how long of an answer you want.
I'm sorry, my German Shepherd just took out my dang second monitor. I was looking at the takeoff thing today, and the first drawing is of the safety shower. So several points here. So it calls out feet in the index sheet at the bottom right hand corner, little index box, and
Mhm.
then the pipe is heat traced. So I just want to make sure you wanted us to take that off and account for that as well.
No, don't worry. If you see any insulation or heat tracing, don't worry about that.
Okay.
That falls under technically a different discipline.
Okay.
I mean,
All right.
insulation falls under insulation. Heat trace could fall under piping if it's steam, but it would fall under electrical if it's electric. So
Yes, it's probably
yeah,
electric.
yeah.
But the other question was, so I even talked to my pipe guy today at work. So you've got your 9 foot of pipe, right? And you're going to add in your little 90 degrees. You got a wedge in there that goes from 1.5 inches to 1.25 inches. It's it's concentric. And that adds to the total length of the spool piece, right? Well, right in the middle though, there's a threaded section. And so I thought we had said that if it was threaded, it was going to be considered filled. So when
It
we do
is.
when we do our takeoff, we'll have to break that drawing into shop and then filled. Is that correct in stating that?
Yeah, all of the drawings will have a field and shop component to it.
Okay. Okay.
Every one of them, they'll have. What you'll need to do is your through fitting length
Right.
be what you have to handle to install in the field. Your
Right.
actual pipe and fittings will be your shop. But since you point out that it's got a threaded fitting in the middle,
Right.
even though you can take it off as one length, it's kind of what I call it the law of averages.
Right. It's be a 10-foot section. You're only use 9 foot of it. So you're gonna have that 10% of waste
Well,
after
but
you're done building it.
you really are going to have 2 5-foot sections versus
Right.
one 10-foot section. But theoretically, when you use your unit hour and apply it to all 10 foot, it's going to be theoretically the same as if you apply it to 5 foot and 5 foot and then put them both in, because you still have 10 feet times 1.5 hours per lineal foot. Ends up being the same.
Okay.
The main thing but that's only your handling. So then you need to make sure you pick up your flanges, your threaded connections, your field welds. All those things have to be included because they're all field activities.
Right. Unless they're welded, then they'll be in the shop, or unless it calls out a field weld.
Yeah. Well, yeah, exactly. Your welded connections are in the shop except for your field welds.
Right. And so here's the other thing, and this might be getting in the weeds, but if you're looking at that 3,000 pound ball valve, and if you look at that like spreadsheet that I sent you, you thread into that two 2 3/8 inches on each end. And so are you wanting us to go to that minute of a measurement when we call out the length?
No,
Okay.
I think that well, if I were lump sum bidding this thing, yeah, we would, but we're not. This is an exercise to understand the principle. And so no, let's not worry about going that detailed. If you go all the way through, the 2 inches not going to impact the essence of the number. But in this case, since it is threaded, that means it's going to be a field installed valve, and
Right.
therefore you need to pick up your valve handling as well.
Right. Right.
Yep.
Okay. I just want to make sure. I thought I knew what you had asked in your instructions, but I wanted to clarify.
No, good questions. There's no such thing as a bad. Well, I guess if
No.
we
I hear them all the time. No.
but all right. Anyone else? Anything else? But we'll talk through the drawings as much as needed Thursday, and if anybody wants to break out into break rooms, we can do that also.